Exercise 203 on page 508, question number 1. Let's have a look at that one, okay? Determine the coordinates of the points of intersection and the area enclosed between these parabolas. So, first of all, well, sketching it, if you're not clear which way around these curves go, it doesn't matter. All I'm going to do is find the area between them, so I subtract one from the other when it comes to the integration. And if I've done it the wrong way around, I'll just end up with a negative answer. So don't worry too much about that. We're after finding the values of y and x, but what we're really after is the x values, because that's going to give us the limits under the curve. Remember, if I were to sketch this, the curves are probably going to look a little bit like this from what we were looking at before, okay? So what I really need is the values for x, because they're going to be my limits wherever they lie. So don't get rid of y in these, x in these equations gets rid of y. So what I want to do is make a substitution to eliminate y. That might well do. It asks in this particular question to find the coordinates of intersection. So you're going to need x and y to get the coordinates. But from the point of view of finding the area of the curve, what you're really interested in is only the x values, right, Daniel? Because they'll give you your limits. Okay? So take my two equations, y squared equals 3x and x squared equals 3y, and I'm going to try and eliminate y. So what I need is y equals something and then substitute that in. So what can I do to make y equal something, which is the easiest one to work with to get y on its own? Square root of 3x, or this one. I would probably go with number 2, and because then if I just divide both sides by 3, I'll have y equals x squared over 3. Okay? So from 2, you're right though, Dan, you could easily have just said root 3x, but that makes it a little bit more awkward to solve afterwards. Okay? Yeah, so from 2, y equals x squared over 3. So now substitute into 1, and we get y squared, which is now x squared over 3 squared, equals 3x. Now I've just got to solve this for x. So what would you do? Yeah. Well, we're going to get, we want to get the right-hand side to be 0. Yeah, but before we do that, I might multiply this out. X to the 4, so that's x squared squared is x to the 4 over 3 squared is 9 equals 3x. Now let's get the 3x over the left-hand side. X to the 4 over 9 minus 3x equals 0. What would I do, Mason, to get rid of this 9 that's underneath? Yeah, but looking at this, how would you get rid of that 9 underneath? Okay, yep. What I might be tempted to do here, get rid of that and just call it x to the 4 multiplied by 9. Multiply that by 9, and 9 times 0 is still 0. Now factorise it, and you'll get the same answer, x cubed minus 27. It just makes it a little bit more straightforward to solve. So therefore, x equals 0, or x cubed minus 27 equals 0. Or if x cubed minus 27 equals 0, which implies that x equals the cube root of 27, which is 3. 3 3s are 9, 3 9s are 27. Yeah. So we've got x equals 0 or x equals 3. Those are our x values. We could now put them in to one of the original equations to find y. But really that's what we're interested in, because these are our limits. So now we need to get both curves so we can integrate them to read y equals something. So the first one, y squared equals 3x, so therefore y is the square root of 3x. And what about this one? Y equals x squared over 3. So these are the two things I'm going to integrate. And we're just going to do one take away the other. So the area equals the integral between 0 and 3 of x squared over 3 minus the square root of 3x. Yep, that's right. Integral between 0 and 3 of x squared over 3 minus the square root of x. Square root of 3 times x to the half, right, Mason? That's what we do with that. So now we just put our limits in and do the integral. Add 1 to the power, divide by the new power, so that becomes x cubed over 9, because we've already got a 3 underneath there, minus the square root of 3 times 2 x to the 3 over 2 over 3, between 0 and 3. Dividing by 3 over 2 is the same as timesing by 2/3, remember. This is a little aside on this one. The integral of x to the half equals x to the 3 over 2 over 3 over 2, which is times 2/3, yeah. And then you put the limits in. The bottom limit is going to be 0. All right, Andrew, we're keeping up here. I'm going a bit quick, I know. So that's going to be 3 cubed over 9 minus the square root of 3 times 2/3 of 3 to the 3 over 2 minus 0. The second limit is going to be 0. So we've just got to work out what that curly bracket is, and that will be the answer. Just as a little extra activity, could you work out what this was without using a calculator, using the laws of indices? Yes, that's right. This equals 3 cubed over 3 squared, because 9 is 3 squared, minus 3 to the half times 2 over 3 times 3 to the 3 over 2. Agreed? Look at the base, how many bases 3 there are. What do I do? What do the laws of indices tell me to do with this? Right, yeah, that's just 3. 3 take away 2 is 1. What do I do with the powers here? Yeah, 3 squared over 3 times 2. What's 3 squared over 3? So that's like 3 minus 3 times 2 is 6, which is minus 3. So we must have done it the wrong way around. So therefore the answer is 3. Okay. So mean or average values. Here is a curve, and let's say we're going, well, according to this diagram, we're going from this point on the curve to this point on the curve. So the question is, what's the mean value for y between these points? So a mean value. Y is changing between this point and this point. So that we could do some sort of average value to represent y. This could be the average voltage if this was representing voltage up here. How do I find the mean value? Well, if you think about what the area underneath here represents, if I find the integral, I'm finding the area underneath this curve. So if I consider that now not to be a curve at the top here, but a rectangle, and draw in a rectangle here, then actually the area I've just found, oh, that's good, the area I've just found, the area I've just found, let's try and do it like this. So I draw the rectangle like that, assumes that it's the base is length x, which is this bit, and y will be effectively the average value, won't it? So if I find the area underneath this curve, this whole area here, it's the same as the area for a rectangle with the same width but height, average value. So what I can say is that the area equals x times some average value for the y, and this bar means average value. Rearranging it, the average value for y must equal the area divided by the x. What's x? It's the distance between my limits, a and b. And written in an integral, what that means is the mean value equals the integral under the whole curve, which is the area, so that's this bit, divided by the width, x. So that's this bit. And so written as an integral, that's all that's saying. It's using the fact that finding the integral between the points a and b allows me to find the area under the curve. So if I divide that area by those limits b minus a, I'll end up with an average value for y, and that's how it works. Instead of saying divide by b minus a, I can say multiply by 1 over b minus a, and that gives us this familiar function, or this familiar form of this to find the mean value. So effectively it's 1 over the top limit minus the bottom limit multiplied by the integral between those two limits of y with respect to x. So if you want to make a note of that, that's the formula that we use to find the mean value here. So let's look at a new problem here. Now, with whoever takes you for the maths when I come back, he's going to be looking at some numerical methods to find the area under the curve. So this might well be one of the methods he'd use. There's Simpson's rule, the trapezium rule, the mid-ordinate rule. There's quite a few different ways to find the area under the curve by a numerical method, which means you don't integrate it, you just do it by dividing the thing up into strips and working out the area altogether by finding the area of each strip, as you'll see. Sometimes you need to do that way, especially if the function is very complicated or if you don't even know what the function is. But anyway, so let's have a look at finding the mean value of this function using integration. So we use the formula y bar, the mean value of y, equals the integral between 0 and 3, because our limits are 0 and 3, look, of the function 3x squared plus 2 with respect to x. And then we divide that by, or we multiply that by 1 over the top limit minus the bottom limit. And so that's what this average value formula tells us to do. Find out the integral and then divide that effectively by the limits. 1 over 3 minus 0 is just a third. What's the integral of 3x squared? Right, 3x cubed or just x cubed plus, good, between the limits 0 and 3. And so that's a third x cubed plus 2x between 0 and 3. Work out what that is, which equals 11. Now, what is that? That is an average value, y bar. If I were to plot this, just to show you what this is telling us, if I were to plot this function, here it is, you might have expected this curve, actually y equals 3x squared plus 2, some sort of quadratic. What we're saying is, if I were to put this into the notes, so we can see it, between 0 and 3, what we're saying is that between these points, 0 and 3, which is here, so this particular region here, then the average value for y between those points is 11, the average value. So if I was plotting force against distance, or velocity against time, or voltage against time as something is changing, I can calculate what the average voltage is during that 3-second period if this was describing the voltage. A very useful thing to do to come up with an average value. What do you do to come up with the average value? You just integrate between the limits that you're interested in and then divide by those limits, and that's all you do, and it gives you the average value. Okay? If we look at curves over a complete cycle, here, for example, then we find that it actually averages out to be 0. And so if we square x, though, we get rid of the negative values, and we get the bottom curve then becomes positive, so actually this switches up to there, and we get this. Okay? So if I now find the average value of that, then I can get a value for the mean value for the voltage, say. So if I want to know what is the mean voltage over a complete cycle, it's no good doing what we just did and integrating between 0 and 2 pi, a function like this, because it'll come out to be an average of 0, which is what you'd expect. Agreed? But I want an actual value for the voltage to represent the voltage. So what I do is I square everything so that I get an actual value for this voltage. So I square everything, find the mean of that, and then finally at the end to square root to get rid of the fact that I squared it. So I find the square root of the mean of the squared values, the root mean squared value. So RMS is to do with that. And I'll leave you to have a look at the textbook and see how that works. Okay?